start? Okay. Is that loud enough? Yes, now the mic is working. Welcome everybody to the physics department. We have an international meeting here for a space mission, and David will talk about this in a second. And because of that, we thought we organize a public talk that the interested audience learns a little bit about the exciting science we here, but also our friends in Europe and across the United States are working on. Welcome everybody. Hi Hank. Hi Hank. I don't want to waste too much time. I just let the last people drop in. And I asked David Tanner here to introduce Professor David Reitze from the University of Florida, both of them, essentially. And David, now it's up to you.
Okay. Yeah, I wandered in a few minutes ago, and Guido said, you have to introduce Dave Reitze. I knew I should have been late. So I've known Dave since in California here for the second. Sometime around 1990 something, 5 or 6, an email was circulated to the faculty by Gaina Mitzelmacher saying, I'm interested in starting a LIGO group, and we both went to the meeting, and the rest, as they say, is history. He was the lead on the input optics for initial LIGO and was spokesperson for the LIGO collaboration and the lead at basically the same time on the input optics for advanced LIGO until LIGO stole him away from us to be director of the LIGO lab. He remains on leave, a professor at Florida, and he's going to tell us about the gravitational-wave astronomical revolution.
Thanks. So first thing we're going to do is a sound check. Can people hear me? Yes, great, okay. Well, it's obviously a delight to be here. This is my academic home. I've been at Caltech for the past 7.5 years, but I spent many a day in here teaching undergraduates. I dare say that many of you in the room are experts. So for you, I will say that I hope you don't underestimate the pleasure of being told something you already know. For those of you who are not experts, I hope that the next hour or so is interesting and you learn a little bit about what I am calling a revolution. So let's start with that. What's a revolution? Well, it's overthrowing a government. That's not what I'm talking about. I'm talking about a revolution is something that changes the way we think about things. It's a dramatic change. It's a paradigm shift. And what I'm hoping to be able to convince you of is that we are indeed in the middle of a revolution in astronomy. So let's get started. The revolution, actually, the one revolution started about 100 years ago when Einstein came up with the theory of general relativity. Now, the view graph has two parts to it. Pay no attention to that green grid there. Just pay attention to the sun and the earth. And Isaac Newton, about 400 years ago, postulated a theory of gravity. It was a tremendously successful theory of gravity. Basically, it says that masses attract each other, and they attract each other by a mathematical relationship, which any physicist can tell you. What it doesn't tell you is that the information has to get from one body to the other. And Einstein, before he came up with general relativity, told us that it has to travel at the speed of light. So these two things were in tension. And how did it get fixed? Well, it got fixed by Einstein. Einstein says there are two quantities. There's space and time, and special relativity ties them together. There's matter and energy. Special relativity ties them together. General relativity ties them all together. General relativity basically says that space-time and matter and energy, I don't want to say they're equal to each other, but I want to say they interact with each other. And now the green grid becomes important because that's how Einstein sewed it all together. General relativity is a theory of gravity that is very geometric. It's very mathematical. People they're still trying to understand the mathematics of it. But the way it works from the picture is that when you have two masses, All right? What the mass does is it interacts with space. So that green grid that you see is space. Now we're imaging it in 2 dimensions, all right, because it's hard to do 3 dimensions. And you should think, by the way, that every one of those intersections, there's also a clock, because it turns out that time comes into this with some relevance also. All right, so that big dimple in the center underneath the sun is basically the prediction of general relativity that says when you put a massive object in empty space, it changes the geometry of space. Space is no longer, in this picture, Cartesian, we would say Euclidean in 3 dimensions. It becomes different. It becomes curved. It becomes warped. And so you see the Earth over there also has a little dimple because it's quite massive also. So the way gravity works in Einstein's theory is that the big massive object, the sun, changes the geometry of space, which then propagates out, all right, and tells the Earth what the local geometry is. So the Earth is rotating around the sun, not because there's this magic attractive force that Newton said, but because the geometry tells it to move in that way, because the sun is dictating the geometry. Okay, so that's sort of General Relativity 101. Now, here's the problem. The problem is that the curvature, all right, is very small. It takes a huge amount of mass to be able to curve space even a little bit. And this is basically Einstein's equation where I evaluate the constant. That constant is 10 to the minus 43, which tells us that gravity is a very, very weak force. How weak is it? Well, you're standing on the Earth. The Earth is about 5 times 10 to the 24 kilograms. So that's about 6 times 10 to the 24 pounds. If I built steps, and you had took enough breaks, you could climb to the moon. You could get out of the Earth's gravitational pull with your legs, all right? And your legs are not that big. They're not that massive. So gravity is a very weak force, and that's what makes this business so tough. Okay, all right. General relativity predicts a lot of interesting phenomena. One of them is black holes, and if you've been reading the news lately, you know there was this wonderful discovery. Actually, it was work that's been done over the past few years by the Event Horizon Telescope, where they image the shadow of a black hole, and that picture is basically the shadow of a black hole in the galaxy M87, which is about, I think, 55 million light years away. It's a beautiful picture because what you're actually seeing is not, the black hole isn't emitting light. It doesn't emit light. It's actually bending the light, in this case it's radio waves, that are coming, propagating around it. So you're basically making an image. And this is the first time that we've been actually able to visualize a black hole. I will come back to this later on. Black holes play an important role in what we're going to talk about. So how do we make a gravitational wave? I'm here to talk about gravitational waves. Well, if gravity is dictated by putting a mass in a space and having that space curve, the waves, the propagation of gravity, comes about from accelerating those masses. So this is a cartoon, all right? You have 2 black holes, all right, in this case. It turns out these things form in pairs and binary systems quite frequently. And what they do is they orbit around one another. And as they're orbiting around one another, they're radiating gravitational waves, as this cartoon shows you. So space is rippling, so the geometry is changing dynamically. That's what's really happening in this picture right here. Now, the other thing that's interesting about this is the dynamics are actually quite accurate in that cartoon in the sense that the black holes, as they are orbiting around one another, indeed any objects that are orbiting around one another, are radiating gravitational waves. And that radiation that carries away energy, so the orbit decays, all right? And eventually they collide together. So these are not the only sources of gravitational waves. There are others. When stars explode, we believe they produce gravitational waves. The Big Bang itself probably produced, well, it did produce gravitational waves, and we haven't detected them yet. But this gives you a sort of a general idea, a canonical idea of what we're trying to look for when we look for gravitational waves. Now, if you're an experimentalist, what are you trying to measure? Well, it turns out you're trying to measure a strain. Right? A strain is a change in length per unit length. So this is delta L. Delta L is the change in length per unit length. And it comes in 2 flavors. We would call these polarizations, H plus and H cross. H is the variable that we use to describe that strain. It's basically you can think of it as the amplitude of the wave. Now, this immediately suggests something. So if you want to measure a strain, all right, that equation tells you basically how to do it, all right? First, you want to measure delta L as precisely as you can. if you're close to some arbitrary point like that arrow is there, you're not going to get a lot of strain because the delta L, or because the baseline is small. But if you're out here, you get a bigger effect because you're not measuring delta L, you're measuring the strain, delta L over L. So this suggests that you want to make detectors that have long baselines. All right. Einstein himself, when he postulated the theory of gravity, he actually wrote in a paper that he did not think that gravitational waves, which came right out of his theory, would have any possible physical value whatsoever. And he was right. And the reason he was right, because in 1916, there wasn't a lot of technology that you could bring to the table to actually try and measure gravitational waves. Lasers did not exist. A lot of sophisticated electronics did not exist. But let's do an experiment just to sort of calibrate everybody in the audience. So this is a mad scientist, and this guy is truly a mad scientist. He's going to take two 1,000, basically 1-ton masses. He's going to separate them by a meter or so, and he's going to spin them around 1,000 times a second. Now, you don't want to be anywhere near this experiment when it happens. You can see that guy, there he is over there. He's pretty smart. He's hiding in case the thing blows up. And the question is, what's the strain? What is that value that I just told, that strain quantity? And the answer is it's 0.34 zeros and a 1. All right, so this is a mind-bogglingly small number. And the reason for that has to do simply with what I just said earlier, that gravity is a very, very weak force. So there are constants such as this Newtonian constant of gravity and the speed of light that come into this. All right, so Einstein was right, and people forgot about gravitational waves essentially for about 40 years until experimenters started thinking about them in the 50s and 60s. And in fact, it was even people who were trying to understand exactly how you would measure a gravitational wave and what kind of experiment that you do. And people like Richard Feynman and Felix Pirani that came together and said, okay, I think I understand some of the concepts behind this. Now, all right, I just hopefully convinced you that this is a really hard experiment, which is why it took 100 years to actually make it work. The question is, why did people start looking for them 50 years ago? And the answer is because they're really fundamentally interesting, and they're fundamentally different from every other kind of information carrier that we have in the universe. So if you think about what do we know about the universe? We know about the universe because of telescopes, photons. They can either be gamma rays or X-rays or light, optical, radio. We know about the universe because of neutrinos. Supernovas, when they explode, they produce neutrinos. A lot of high-energy astrophysical events, neutrinos. And they've been known for a long, long time and detected for a long, long time. And then, of course, you can look at the other scale. Instead of on universal scales, look at the very subatomic scale. And we have large, basically massive particle colliders, like the Large Hadron Collider. All right, and all these things provide information that you can't get without having them. But gravitational waves are fundamentally different. And they're fundamentally different for the following reasons. First, they don't look at the things that these guys look at. They produce basically by moving masses, accelerating masses. And in fact, in order to detect a gravitational wave, as you'll see, you need really violent astrophysical events. All right? They travel unimpeded through matter. You're actually being bathed by gravitational waves right now. Fortunately, the amplitudes are so small that you don't know that. And they carry unique information that you can't get from these other kinds of sources. So that's why we've spent lots of time and people's careers trying to detect them. All right, so here's a source that can be detected, and I'll come back to this later because it plays an important role in the story. Nature does the same experiment as the mad scientist, but in this case, nature is using 2 neutron stars. These are basically the dead cores of massive explosions when stars reach the end of their lives. They're roughly the mass of the sun, maybe a little bit heavier than the mass of the sun. And they also form a lot in binary systems, in pairs. And they do the same sort of orbital dynamic that I just showed you before and that the mad scientist tried to do. In this case, you can calculate that the change in length that you would, or the strain, that you would measure, is about 10 to the minus 21. Now, I'm making some assumptions about where this is. These guys are about 500 million light years away, so they're pretty far away. But nevertheless, it's still a tiny, small number, but at least it's something you can actually look at and say, well, maybe we've got a hope. All right, so Now we fast forward. In 1987, the National Science Foundation, which plays an important role in this story, funded a group from Caltech and MIT, at the time led by Robbie Vogt, Ray Reitze, Kip Thorne, Fred Robb, and Stan Whitcomb, to build a gravitational wave detector. All right, an interferometer, which I'll tell you how that works in a few minutes. And that interferometer's job was to try and detect the kinds of sources, this binary neutron star, this binary black hole, and other sources here. So it took a long time. 2 observatories were built. This is the observatory in Livingston, Louisiana. So it's about, 500 miles from here, down here. The arms are 4 kilometers long. All right, so this is in the language that I was using before, this is the baseline over which you're measuring the gravitational waves. And you'll notice that there are 2 arms and they're perpendicular to one another. Here is the almost completely identical observatory. This one is in Hanford, Washington, so it's in the northwest corner of the United States. And it's, again, 4 kilometers arms. And now let's come back to that concept of strain. So the 4 kilometers in this case is the L in the denominator. All right, so basically we're trying to measure a strain using over a 4 kilometer baseline. I'm going to challenge you on a Sunday evening to do a little math. 4 kilometers is 4,000 meters. I said a few slides ago that we're looking for signals that are on the order of 10 to the minus 21, give or take. So what does that actually mean in terms of delta L, in terms of the precision that you must measure the change in length? And the answer is about 10 to the minus 18 meters. All right, put that in perspective. A nuclei, a nucleus of an atom, nuclei of atoms are about 10 to the minus 15 meters. So this is about 1/1000th the nucleus, the diameter of a nucleus of an atom. To put it in another way you can think about it is different people have different ways of saying this. One I like is if you were to measure the distance between here and the nearest star, which is Proxima Centauri, it's about 4 light years away if I remember correctly, it would be this basically equivalent to measuring the precision to the width of a human hair, which is about 100 microns. So these are incredibly precise measurements, and they're incredibly hard to do, which is why it's taken so long for people to do them. All right, how does it work? Well, we use a technique called interferometry, which is very tried and true, and I'm going to play a movie here in a minute, but I'm going to set it up for you. This is our laser. These are the 2 arms that you saw before that were 4 kilometers long. This is a beam splitter. It basically takes the light and divides it into 2 equal parts, sends one part perpendicular and the other part parallel to in the original direction. Over here is we call it a photodiode for the purposes of the illustration. It's basically a screen. All right, and what we're trying to do is measure the stretching and compressing of space and time. And an important point, and maybe you noticed it, maybe you didn't, when I was showing that cartoon of what we're trying to measure, is that the strain is differential. In other words, as one arm of the interferometer or one dimension is expanding, the other dimension is simultaneously contracting at the same time. All right, and remember, we're trying to do this to the level of about 10 to the minus 18 meters. All right, so here's the cartoon. So this laser is a very precise laser. It produces 2 wavelengths. We color code the wavelengths. In our case, they're about 1 micron, so about 1/100th the width of a human hair. They come back and they interfere, and because they're coherent, we set up the arm length such that no light gets back to that part over there, this part here, which is the beam splitter. But as the photodiode. As a gravitational wave passes, however, the arms stretch and compress very, very minutely, but they stretch and compress. And so what we do is we actually record the change in the intensity of the light due to the dynamic interference changing due to the passing gravitational wave. All right, the concept is kind of simple in that regard. It's very difficult when you actually try and implement it. And the point that I'll make here is that in this illustration, in this cartoon, we were showing the wavelength shifting by about 1 micron, in other words, 1 whole wavelength. In fact, we have to measure things to a trillion times better than that, about 1 part in 10 to the 12 of a wavelength, 1 part in 10 to the 13. So that's quite challenging. All right, here's how we do it. So let me go back to So this part of the interferometer here is actually here. Okay, so this gives you a sense of the complexity. The laser is actually back here. I'll do it up here. The laser is back here. The beam splitter is right here. All right, one arm of the interferometer goes this way, the other arm goes this way. The photodiode, the thing that records the light, is down there. All right, and there, if you go 4 kilometers in either direction of the direction of either arms, you would actually see more equipment. You'll notice there's a lot of tanks here. The interferometer is actually completely in a vacuum system. That's actually very important for us. There's 2 points that I should make right now. The first point is that interferometers, if you think about a telescope, you think, oh, I can point it in a certain direction and I can see, with some angular resolution. And telescopes actually have very good angular resolution. Interferometers don't. All right. In fact, they're very poor. And the analogy that I can give is they're more like a microphone than a telescope. Gravitational waves coming from any different direction, all right, almost any different direction. There are a few special places, but almost any different directions will record as a signal. So one interferometer is alone not enough to actually identify where a source is coming from. And I want to stretch the fact that I use this analogy of a microphone a little bit further. Turns out that for LIGO, for the gravitational wave detectors that I and a number of people in this room work on, the audio analogy is quite apt because the signals that we receive actually are in the frequency band that covers our ear span from about maybe 10 to 20 hertz to a few kilohertz. All right. That will become important later on. Okay, so let's look at some of the technology. So in order to make this work, we need a lot of sophisticated technology, and that's what took a lot of time. The laser was built by the Albert Einstein Institute in Hanover, Germany. It's I believe, the world's most stable laser. And you can see that to work on it, you need to wear these bunny suits because you have to be very clean. There's seismic isolation. The Earth is a very noisy place, and we're trying to measure things to a tiny fraction the diameter of a nucleus of an atom. So we have to go to great pains to basically seismically isolate the mirrors in the interferometer. Then there are the mirrors themselves. These are, we believe, some of the world's best mirrors in terms of their surface figure. And you might say, well, they don't look like they're totally reflecting. That's because of the wavelength. In this case, green light goes through them, but infrared light does not. This is about 1 micron infrared light. And then finally, these mirrors are suspended on glass fibers. And these glass fibers, actually, each mirror only contacts the outside world through 4 very tiny glass fibers that are about 500 microns in diameter. And the reason we do that is that, again, we have to isolate the mirrors, but the mirrors themselves have to be free from any disturbances or any forces that would move the mirrors more than a gravitational wave would. So we try and basically make the interferometer very quiet and get it so quiet that none of the forces, such as, for example, the fact that the ground is moving, or maybe that there's a lightning strike and there's noise, acoustics, anything that could cause the mirror to move, we try and get rid of it. And we're pretty good at it. We're not perfect at it, but we're pretty good at it. Anyway, you put it all together and it actually works. And I'll point out that there's a huge team of people that actually made this work. Myself, I'm here at Florida and also at Caltech and MIT. Played a role in this, but also a much larger collaboration of people that built different things. So the suspensions were designed by the University of Glasgow. The seismic isolation system by Stanford. Florida was part and parcel of the input optics, which I don't show here. So this is really a big, huge team effort, and that's actually something that's very important. There's a lot of engineering that goes into this too. Okay, let's get to the excitement. So we're actually on our second generation of gravitational wave detectors. This one is called Advanced LIGO. The first generation, you can actually go out into the atrium and you can actually see pieces of the first gravitational wave detector, initial LIGO, which worked but didn't actually detect any gravitational waves because it wasn't sensitive enough. But you can get a sense of some of the technology here. All right, the first event that we detected was a binary black hole merging, and it was a wonderful event. And it turned out that it was 2 black holes. One was about 36 times the mass of the sun, The other was about 29, so call it 30 times the mass of the sun. And they were actually about 1.3 billion light years away. All right, the signals that we saw, this is the signal that was recorded in Hanford, Washington. This is that quantity strain, so you can think about that as h, that quantity. And here's time, and this is seconds. So you can see that this is a really brief signal. It's a blip. There's a huge amount of information contained in that signal. If your eyes looks at it, you can certainly see certain features that become sort of apparent. More importantly, there's enough information in that signal that with using the coincidence signal from Livingston, and I show the blue overlaid on the red here, this is blue is Livingston, red is Hanford, you can actually extract the parameters of the gravitational wave source, in this case these two black holes. And in this case, you can actually solve Einstein's equation. So this goes back to general relativity. And you can visualize, you can make a visualization of what we actually saw. So I'm going to play you a movie, all right? And it's a movie that basically was, it's basically a movie of the event that generated these signals. And you see there's stars in the background. The stars are there just for your reference frame. So let's go ahead and play the movie. All right, you see these two black holes, and you're looking at them face on. In your case, you're about 1,000 kilometers from them. You're looking at them face on. You see they're getting closer and closer and closer together, and eventually they merge, and then there's this big burst, this boom of gravitational waves. All right, and then what's left behind is one final black hole. All right, that's it. That was what happened, and what we saw was about 0.2 of a second of that event. Now, these orbits had been happening for a long time. The system had been radiating energy for a long time. It's only in the last second, less than a second, that it comes into our band. In other words, that the frequencies that it's emitting are sensitive to the frequencies that we can detect using LIGO, all right, and we see it. It's a remarkable event because in that last fraction of a second, I think it was 0.2 of a second, basically the equivalent of 3 solar masses disappeared. In other words, the two original black holes created this final black hole, which was about 62 solar masses, but it also radiated away 3 solar masses. All right, so basically, take the mass, 3 times the mass of the sun, turn that into energy, and blow it away. And you might ask, how do I compare that to, power output of the galaxy? And the answer is that, power output of the universe. And the answer is that this event, when it happened, was brighter than the entire quiescent universe, the entire EM universe. So these are tremendously, tremendously energetic, powerful events. But because they're dark, because we don't believe that black holes are going to emit light, 2 of these black holes, we can't see them any other way, and you can only see them in gravitational waves. So now I'm going to show you the same data. I'm actually going to play you the same data, but I'm going to play it a little differently. All right, this is called a spectrogram, and I'm going to basically take the output of the interferometer, and this is the real data of the interferometer. It's been filtered a little bit, and I'm going to play it back so you can actually hear it, and I'm going to play it 3 times. Okay, so you heard that thump. That thump is basically the ripple of space-time as it passes through our detector. All right, and it's remarkable, at least to me, to think that these 2 supermassive black holes that are ultra-compact, that are 1.3 billion light years away, the event propagates all the way to our detector and then goes thump. All right, that's it. Now I'm going to play it again. We've learned to take a page from astronomers. They like to use false color. So when you're looking at the image that I showed you, the black hole, those were actually radio waves, but they were orange. All right, so I'm going to do the same thing, but we're going to do this with sound. So I'm going to upconvert. I'm going to shift the frequency up by about 400 hertz. Okay, you hear that whoop, whoop. That's called a chirp. All right, and that's the sound, in quotes, that's the signal that these coalescing binaries make when they come together. Now, you can see the waveforms actually have a lot of information in them. Basically, that chirp is clear in the frequency. The frequencies are getting faster as you get to later times. And then everything disappears, and that's because you've created a final, basically the 2 objects have merged and you created a final black hole. Okay. Since that time, we've detected actually now 13 more, or 12 more. We have 13 black holes. And I like showing this plot because there's a tremendous amount of information on the plot. Let me walk through it. So the y-axis is mass in terms of solar masses. So every one of those dots on here, the purple ones and the blue ones, are black holes. The blue or the cyan ones are black holes that were discovered by LIGO and Virgo. Virgo is an interferometer that we work with, a very important interferometer in Italy, that were discovered in the last 3 years. All right, the purple dots, or the purple, are black holes that have been discovered over the past 40 years, roughly, using X-ray astronomy. So I said black holes don't emit light. That's true, but often black holes form in pairs where they have another star, and basically that star is big, and the black hole, if it's in the right place, it'll start sucking. It's like a vampire. It'll start sucking matter off of the star. All right, and that matter accelerates and gets very, very accelerated. Accretes is the word we use on the black hole, and it produces a lot of bright X-rays, and you can see those. So that's what those purple ones are there. All right, the first thing to say is if you count the number of purple dots and you compare that to the number of blue dots on that graph, there's more blue dots. All right, and that's because LIGO Virgo has discovered more gravitational waves than the EM astronomers. Not so surprising, since black holes are hard to detect directly. The other thing, we kind of cheat, right? We get three black holes for one every event. You know, we see two, they come together, they die, they're gone, and we create a new bigger black hole. That's the first thing. The second thing that you'll notice is that there's a skew in the spectrum, right? So if you look at the mass, all of the purple black holes, which I should point out are all galactic. They're all from our galaxy, the Milky Way galaxy. All tend to be less massive than the ones that LIGO has detected. So LIGO and Virgo have detected sort of a new class of heavier stellar mass black holes. Now I should point out that black hole that I showed you earlier, that's a supermassive black hole. It's about 6 billion solar masses. It's a completely different class of black holes. I'll say more about that when I talk about LISA later on. And this, as I said, is out of date. In the last 3 weeks, we've just been running with a new and slightly upgraded advanced LIGO and advanced Virgo, and we've seen 3 more of these kinds of events. So we're now up to, I think, about 39 black holes. Okay, now that was really quite, we thought, revolutionary, that you can actually now do black hole spectroscopy. But the other revolution happened not much after that, and it's called multi-messenger astronomy. And it's all about the power of networks. All right, so remember that I said that one interferometer is very bad at getting the source location. All right, 2 interferometers is a little bit better. 3 interferometers is a lot better because you can triangulate. So by basically measuring the time difference of the waves as they pass through the interferometers, and you record those waves, by looking at the differences in times, you can actually triangulate, much like we triangulate here on Earth. And in fact, that's very important because, well, first of all, we have a number of different detectors that can do that. So here's the 2 Livingston LIGO detectors I showed you. Virgo, I mentioned, it's a detector in Italy. There's a GEO detector, GEO 600 in Germany. And then there are 2 interferometers, one under construction in Japan that will be operating hopefully this coming year, and then one in India that's planned for 2025. So why do we build these big, complicated detectors? And one of the reasons we build them is so that we can have more detectors looking for these events and being able to see them, all right, more accurately and in a more localized manner. All right, so why that? Why should we do that? And the answer is because not all objects like black holes are dark. All right, coming back to these neutron stars, all right, that I showed you very early in the talk, these neutron stars actually, they are much more complex than black holes. Black holes are actually pretty simple entities physically. Neutron stars are more complex. You can think of them, as I said, they're sort of the dense hull of the remnant of a supernova. And they're basically solid atomic nuclei, but much more massive. So they're made up primarily of neutrons, but they're nuclei that have masses 1.5, maybe even up to 2 times the mass of the sun. And so because they have matter, all right, when they do this, I'll call it this dance of death before they collide together, all right, when they collide, all right, they actually release not only gravitational waves, in fact, they're doing that right at the point there, they release everything else, all right? And so they release light, they release neutrinos, we believe, we haven't seen that. So if you can actually see them, if you can basically detect them using the gravitational wave detectors, which we see the signal before, and tell our astronomy partners that, hey, we see a signal that's kind of over there, all right, they can follow up and they can look at that. And what they will see is spectacular. All right, now, here's the problem. The problem is even with 3 detectors, in this case this is actually 2 detectors, the error boxes, in other words, the precision that we can see things is not very good. All right, so this is an event that actually we recorded last Thursday. We believe there's a good chance that it's a binary neutron star event, which means it should be emitting not only gravitational waves, but other sources of electromagnetic radiation. Unfortunately, if you're an astronomer that has a telescope, you can look at this, and this is basically the entire sky. This map that I'm showing you is the entire sky, and you can ask yourself, where should I point my telescope in that sky? And the answer is not obvious, right? Nevertheless, people are actually looking at this event because it could be very exciting. If they can see it, here's what they'll see. All right, this is a simulation from NASA actually showing what happens. All right, this is not a mathematical simulation. It's really a movie. When these 2 neutron stars are combined. Boom. When they combine, they produce a burst of gamma rays that comes off sort of in a beam direction perpendicular to the orbit. They produce huge clouds of very dense atomic nuclear matter that can undergo a lot of nuclear reactions called R processes very quickly. They produce blue light, they produce radio waves, they produce basically every kind of electromagnetic radiation. And the reason I can say that is because we know that, we saw one. All right, on August 14th of 2017, we saw our first binary neutron star event, and this is a really important one because this is this power of using photons and using gravitational waves. So this is a map, all right, showing the different localizations. So if you use, all right, I should be a little careful here. Fermi and Integral are gamma ray satellites. And when they look, they were able to localize a gamma ray burst in this region. This is another localization. LIGO alone, the 2 LIGO detectors, is able to localize in this region, right? But when Virgo comes in, and this is why that 3rd detector is so important, Virgo is able to localize here. And if you see that's totally consistent with all of the other localizations. So instead of finding a needle in a haystack, now we're trying to find a needle on a table, okay? It's not nearly as hard to do that. And in fact, that's what happened. So let's go ahead and run the movie. So we identify the error box here. The astronomers get to work. There are 50 galaxies that are in that error box that are about as far as we could possibly detect a gravitational wave. They hone in on one, and they hone in on this galaxy. It's NGC 4993. It's about 140 million light years away. It's an elliptical galaxy. You know, it's a nice galaxy. But what they see, all right, is this. All right, that dot there was not there before we saw our gravitational waves and Fermi saw their gamma rays. So that event, all right, was the first observed event of a binary neutron, of 2 neutron stars colliding. And they collided about half the speed, a third of the speed of light. They're actually quite energetic. All right, but it produced light across the electromagnetic spectrum. And this was a fantastic result. It was fantastic in a lot of different ways. As of right now, I believe the last time I checked, there were about 1,500 academic papers published on this event. 1,500. All right. One of those papers, all right, was published by the LIGO-Virgo collaboration in conjunction with the astronomers that did the observations. That paper had 3,500 authors on it. I can tell you, if you've ever written a paper with 3,500 authors, it is a very, very complicated thing to do. And we did it in 2 months, actually. All right, why is this event important? It's important not only because we saw the first binary neutron stars, because it gives us clues to where elements come from. All right, so this is the periodic table. And you'll recognize it. It's color-coded to show you where astrophysicists and nuclear physicists believe elements were formed. All right, the Big Bang formed hydrogen and helium, so that's coded in red there. The lighter elements, some of them were formed by cosmic ray fission. Most of them were formed by basically exploding stars, supernova, white dwarfs, things like that. Then there's all these heavy elements, the lanthanide series and things like that. And up until this discovery was made, there was a conjecture that things like gold, elements like gold, like platinum, like uranium, came from the collision of two neutron stars, but there was no hard evidence to suggest that was the case. And after our, this large group of astronomers' observations, in fact, it was verified that these are sources of these heavy elements because basically you have a very dense and rich nuclear environment, and you need that density of nucleons to be able to produce the fusion that allows you the elements to fuse and get the heavy elements to hang together. Now, what we don't know is if all of the elements in each of those categories up there came from binary neutron stars. Chances are they don't, but the jury's still out on that. So there's still a lot of work to be done understanding that. So that's quite exciting. All right, now what I want to do is switch gears. I've told you about the revolutions that have happened in the past 3 years, which were 100 years in the making. Now I want to talk about the future. So what I've talked to you about so far are ground-based observatories. Right, but it turns out the gravitational wave spectrum, much like the electromagnetic spectrum, is not just made up of gravitational waves that can be detected on Earth, but there's a whole spectrum, and you can think about it in terms of the periods, all right, which is another way of thinking about waves. So LIGO and Virgo detect wavelengths that have periods, or waves that have periods of milliseconds. Like I said, it's in our audio band. All right, if you shift down, there are longer wavelength events that have periods from minutes to hours, and that's going to be the subject of the next few slides. You can even go further. There are gravitational waves that have periods of years to decades. These are, if you think about it in terms of wavelength, these are sort of galactic scale. And then there are gravitational waves that have periods of billions of years. In fact, these are the gravitational waves that were produced at the beginning of the universe in the Big Bang and implanted them and sort of embedded themselves in space-time. And in fact, these have wavelengths fractions of the scale of the universe. All right, there are efforts to detect all of these kinds of different sources, but I want to focus on this one because this is the next one of the next exciting frontiers. And the reason that many of us are here for this LISA color project. LISA stands for Laser Interferometer Space Antenna. It is the same kind of idea as LIGO. It uses interferometry, but it does it in a much more sophisticated way, and it does it in space. And the first thing that you'll notice if you look at that picture there, that picture is an artist's rendition of what LISA will look like. All right, the colors are false, but when it operates in space. So it's a triangle. It's not an L shape, and that's okay. You can do interferometry with triangles. All right, let me go back here. LISA is a concept that's been on the books for many years. I think it goes back into the 1990s. The experts here will be able to tell them. It's really exciting science, but it's really, really complex because you have to build satellites that get launched. So this mission horizon is basically also measured in decades. LISA, well, let me take you through it. I'm going to show you a movie. This was produced by, I believe, ESA. This is what LISA will do when it's launched. So you've got to get it off the Earth. You've got to get that interferometer off the Earth. Here's how you do that. It launches. The package deploys. All right, and you will see that there are 1, 2, 3 spacecraft. 3 spacecraft that get sent out. They leave the Earth's orbit. There they go. And they travel. And I don't remember exactly how long they travel for, but it's a long period of time because they have to get pretty far away from the Earth. And then they deploy, and this is basically the interferometer package on the spacecraft. You can see the solar cells there. They turn towards the sun so they can get energy. You'll see there's a radio dish there. They have to turn towards the Earth so that they can receive signals from the Earth. And by the way, there's not one spacecraft, there are 3. You can see those ports. Those ports are where the lasers come out. All right, now it's getting signals. You know, it's sending telemetry data, it's receiving instructions from the Earth and what to do. Then it has to configure itself, all right? And it configures itself by sending beams of light to other spacecraft, all right? And in this movie, the arm lengths are not 4 kilometers, but they're 5 million kilometers. I think the current version of LISA has them 2.5 million kilometers. So you have much bigger baseline. And it's also in space. So now they're trying to orient themselves. The spacecrafts have to sense the light and then have to use that to be able to orient themselves, basically, to the proper position so they can capture the light. And then one arm of the interferometer is established. All right, now we've got to get the next arm going. Right? And so that's what happens here. Light is sent out to the other spacecraft. And by the way, this is all very complicated because these spacecraft are very far away, as I said, 2.5 million kilometers, and they're moving. So by the time you send the light, it takes the light probably about 8 seconds to get over there. And you have to know where the spacecraft is going to be before you send the light. So there's a lot of complicated telemetry that has to go on here and motion sensing that has to go on here. And eventually, they all lock up, and now you have your LISA interferometer. And you can ask yourself, where is it? Well, it's actually not very near the Earth. It's in a trailing Earth orbit. It's about, I think, 15 degrees off of the Earth with respect to the sun. And it follows the Earth around. And the simulation will show here. There are the spacecraft. All right. And there it goes. It's sort of like this pinwheel that's going around and around and around. And that makes life complicated, too, because the spacecraft are moving, all right, the gravitation, basically everything is Doppler shifted. So you have to worry about, the Doppler shifts in the light and things like that. And there's very sophisticated interferometry, which I don't have time to talk about, how they recombine the signals from the different spacecraft to be able to actually extract the gravitational wave signal. It's really, really a tour de force. What is different about LISA? All right, LISA will do things that LIGO cannot. LIGO tries to test general relativity, and so far we've tested it and been able to say that general relativity is right. We can't test it nearly as good as LISA can. So LISA can look at much heavier objects like intermediate mass black holes. And in particular, it can look at what are known as extreme mass ratio systems, where you have a very, very heavy black hole and a very tiny black hole that's orbiting around it. And in the parlance of physics, we would call that tiny black hole a test particle. And what that test particle can do is it can orbit around the space that's warped by the massive black hole and basically make a map of the space-time. And the gravitational waves that are emitted as that object moves around basically give you the map of space-time there. And if there are deviations from general relativity, you might be able to see it through this particular kind of event. Back to this supermassive black hole. One of the questions one can ask oneself is, how did these big supermassive black holes, this one, like I said, is about 6 billion solar masses, how did they form? In our galaxy, we have one that's about 1 million solar masses, 5 or 6 million solar masses. Well, did they form through a lot of binary collisions? Did 2 small black holes come together and form a binary, and then 2 more, those 2, I think that some hierarchical effect, or did they form from some other way? Well, until you can actually look inside the region between where we see where LIGO sees its black holes, and where these supermassive black holes exist, you can't know that. And LISA will be able to answer that question, we hope, very definitively. LISA technology is amazing. I thought LIGO technology is amazing. LISA is really amazing. And these are just a few of the excerpts if you go to their website. The one that I really like is they have mirrors also, but their mirrors look like this. This is a 2-kilogram piece of gold and platinum it's overcoated by gold. And it is the test mass. It is the thing that reacts to the passing gravitational wave. Now, each one of those spacecraft has not 1, but 2 of those objects in them. And they're supposed to be free. So the spacecraft has to do a lot of work to sense where those masses are, get out of the way, and it has to do it in both, with both masses. So they've got very, very sophisticated protocols to be able to do that. Here's the optical bench on one of the spacecraft. It's actually duplicated on all of them. And in order to get the spacecraft out of the way, you have to and I love this, these spacecrafts are very, very heavy. You know, they're thousands of kilograms. You have to exert micronewtons, which is basically like going, like blowing out of the spacecraft to be able to move the spacecraft around. It's quite remarkable. It's going to be a very, very exciting mission. And we know it works, or we know it's going to work, because over the past few years, in 2015 and 2016, when you do something this big, you have to test it out. They set up something called the LISA Pathfinder. It didn't go out beyond the Earth's orbit. It was close in. It was one of the Lagrange points. And they tested most of this, and it worked spectacularly well, much, much better than they even envisioned it would work. So all the technology is basically there. Now you might say, when's LISA going to work? It's going to take some time. The launch date for LISA is 2034, and that's predicated by a lot of different things. One is budget, how much money you have to build. One is there's a lot of designs that need to happen to be able to make it work. Okay, I'm going to finish with, this is the end of the revolution, but I thought this would be fun. In the past 3 years, because of the discovery of gravitational waves, they've migrated into pop culture and other cultures. So you can see Sheldon Leonard from the Big Bang Theory. It's hard to see, but that's the gravitational wave. That's the cartoon I showed you. A number of different cartoons. Here's Stephen Colbert talking to Brian Greene. This gentleman is from Australia. He's an Olympic swimmer. He has a bathing cap that has the gravitational wave on it. You can buy gravitational wave fashion now. I think that's kind of cool. In New York City, and you can still see this. This happened about 3 years ago. They used gravitational waves as an ad campaign. A number of op-eds in many newspapers basically talked about the importance of doing this kind of what I call swing for the fence science. Saturday Night Live did a skit on gravitational waves. A great book. They're one of many. There are a number of books that have been published on this. Art, people have written music using our chirps. People have done art inspired by this. 2 heads of state have tweeted about the importance of this. So this has really permeated quite far. But my favorite is this. And this happened in the Guardian UK the day after we made our announcement. That was February 11th. This is February 12th. This is an excerpt of a cartoon, and I'm going to read it to you. It says, obviously we cannot see these waves. The only way we know they are real is by having another extremely sensitive device which detects scientists having feelings of excitement. All right, so you can see here, all right, that this person is very excited. He's detected, or she's detected, a gravitational wave, whereas this person here has eaten a cheese salad sandwich, and they're obviously quite excited too. My favorite part of this is this, because it's so wrong. It says, fun fact. Scientists' emotional reactions are also the fraction of the width of a proton. I can assure you that that is wrong. And with that, I will take some questions. I hope I've convinced you that this really is an exciting time in a revolution. Stay tuned. A number of acknowledgments. There are some logos here. Again, I point out that all the work that I've talked about was the work of the LIGO Virgo collaboration funded by the NSF. LISA, of course, is funded by ESA and NASA. So it's really quite exciting. And for more, there's many websites that you can go to. So thank you.
Questions?
If you're an expert, you can only ask a question that the public could ask, though, okay? That's fine.
No expert. You conveyed how faint the gravitational waves are, and you gave some explanation about at Louisiana and Washington ways in which it's set up to eliminate interference from stuff on our planet.
Right.
But it seems mind-boggling, given how faint the waves are. Is it possible to explain any further for us lay people how it could be isolated that well?
Sure. So the question was, these waves are very faint. and we have detectors, and how is it that we can really make a detector that's capable of measuring the feebleness, if you will, of the gravitational wave? And there are a number of things we do. We start with calculations. All right, the first thing we do is okay, what are all of the noise? All right, what are the possible ways that the interferometer could fool you into seeing that you have a signal? And there are a number of different ways. One has to do with the fun, and by the way, I should give credit here. The person who really figured this out first was a professor at MIT, Reitze, who was one of the Nobel Prize winners in 2017. He wrote a paper in 1972 that's really a remarkable paper because it walks through I think there may be one or two things really right. Okay, so the thing is, you have to understand when you generate laser light, wavelengths are not perfect. Lasers aren't perfect, so you have to understand how they fluctuate both in amplitude and frequency. You can do that. I think I lost my. Is there another mic here? No, it's still there. Okay. We can make interferometers, but we can't.
Give me this, I'll take it to the boss here.
Okay. So isolating from seismic motion. That turns out to be a big challenge, and we do that in a couple of ways, and I just sort of hinted at it. First, we have active seismic isolation. So we basically have seismometers around the floor of the interferometer that read out the motion at low frequencies, all right, and then send a signal to a platform that has actuators that cancels that. You can think about it as sort of active stabilization, like your Mercedes-Benz has, shock absorbers. All right, we do that a couple of times. There's multiple levels of that. And then the last thing that we do is we make this suspension. We use the fact that pendula have very well-known, we call them transfer functions, but basically if you excite the top of the pendulum, all right, you can calculate exactly how far or what the response of the bottom of the pendulum will be, and we do that, we calculate it. We have to calibrate we don't trust that the calculations are all right. We have to calibrate the detectors. That's a very complicated process. There's a huge number of feedback control loops. We have to keep the interferometer mirrors very, very accurately positioned. I didn't talk about the details of the interferometer, but there's I think 350 control loops in here that have to be all understood and calibrated. There's a big vacuum system. One of the sources of noise is when light travels through atmosphere, it scatters, and if it scatters, it loses information that a gravitational wave gets to it. So there's a number of things like that. There are a lot of good websites, actually, if you're more interested in this, that actually walk through sort of at a level that I think is quite understandable how they attack that problem, how we attack it. So.
We may have to share our mics, but
are there advantages and is there interest in southern are there advantages and is there interest in a southern hemisphere array?
Testing. Okay. Yeah, the question was. Are there advantages to having a detector in the southern hemisphere? And the answer is yes. The baseline over which you can separate your detectors, the more angular resolution that you get. At one point, we had thought about putting a detector in Australia. Turns out these detectors are quite expensive, so getting them funded is a challenge. India turns out to be not such a bad place, and that because it's far enough south that it actually gets about 75% of the goodness of putting something in Australia. So maybe you can make this work. Let's try.
The signal looks very sharp. That's the going out, and then back in, that's 0 plus and minus. Is it that sharp? Is it instantaneously changing direction?
Yeah, so the waveform that I showed you, I mean, there's a little bit of noise on it, but the waveform that I showed you is in fact the signal that's recorded. So the sharpness has to do a little bit with the digitization. You know, the data is a little bit digitized and things like that. But yeah, it's a pretty good, you know, and high fidelity representation of the waveform. So a lot of it, the noise superposes on that, and the sharp features that you see.
Other questions? Here's one. Push the button.
All right, so for Lisa, if one of the 3 detectors fails, is there any way to salvage the project, or are we just done for at that point?
Yeah, my understanding is that all 3 spacecraft need to be working, right? And if one fails due to some, you know, communication mechanism or some internal problem, that would be a showstopper.
Other questions?
Which I'll follow up with that, which is why people are taking great care to make sure that there's a lot of redundancy and things like that, so that you know, the possibility of that happening is, you know, as small as you can possibly make it.
Would like to know if LIGO is able to tune the detector if they would know in advance what kind of signal is about to show up. Can you like shift the frequencies in a certain range to be more sensitive there?
Yeah, so the question was, can we tune the detectors to shift the frequency if we know the source? That's a very sophisticated question, and it turns out there's thinking about how to do that, but it's not so obvious. Without going into too many details, the interferometer that we've made actually has the capability of changing its frequency response and making it more sensitive in a certain narrow band at the expense of some of the other bands. To do that, you need to actually change a mirror, and that's one of the mirrors in the interferometer, and that's quite complicated. There are reasons that one would want to do that, and for example, if you could follow a binary neutron star merger, you could actually sort of sweep, as it's sweeping through its frequencies, you could sweep through the interferometer frequencies and basically see as sensitively as possible all the different phases, particularly at the end stage when it merges together. It's a great question. It's not obvious how to do that, but people are thinking about it.
Let's thank Dave again.
Okay, I think it works now. I figured it out. 1 out of 3 occasionally. So for everybody who has the entrance pass for that little reception over there, that way. Follow us that way. And for the general audience, thanks for coming. And we might repeat that again.